And without further ado, I'm very happy to call him up on stage, and please give a big round of applause for Daniel.
First of all, thanks for inviting me and giving me the opportunity to talk here at this super nice speaker series. I'm very excited to tell you about our work that we've been doing at Microsoft Research. So the title of my talk is MatterGen, which is the name of our model, and it's a generative model for inorganic materials design, and we'll talk about what that means. But before I go into any detail, it's very important to highlight that this is a super collaborative effort. Many people contributed to this work. Fantastic team and great project. And this is only a subset of all the people who contributed. Okay, so why should we care about materials design? Many people believe that materials design could solve or could help solve many of the challenges that humanity has by developing better batteries, solar cells, by capturing CO2 from the atmosphere, or by improving quantum computers. And one of the central questions of materials design is how do we obtain a material that is both that we can make, because many of the things that you would like to make we just aren't stable. They decompose once you've made them, or you can't even get there. And so you can make it, and also it has all the properties that you would like it to have. For example, certain electrochemical or mechanical properties. And many other desiderata, so it has to be stable over time, shouldn't degrade performance, and so on and so forth. And traditionally, how people address this is via screening, where basically you have a large database of, let's say, 100,000 candidate materials, and you have methods to predict their properties or to estimate their properties, or maybe somebody has made the stuff and measured the properties, and then basically you just funnel down and filter down all these 100,000 materials based on your properties you have at hand until you arrive at maybe 5 to 10, which is roughly a number that you could then give to an experimentalist and tell them, hey, can you please try to make this? And once you've made it, can you try to see whether it has all the properties that we want? And very recently, just end of last year, there's been an exciting development by Google DeepMind, where they have proposed roughly 1 million new candidate materials that they proposed, and they computed the stability with some pretty good computational tools that now could also be used for screening. But it's important to say that these 1 million materials, they haven't been made yet, so we don't know whether you could actually go into the lab and make them. But it's very useful for scientists going forward. There's also been some work at Microsoft. So this is from Microsoft Azure Quantum, where they basically proposed a new candidate material that could be the basis for a new battery cell, and they basically compressed what would have taken years or even longer, maybe decades, into basically just a couple of days of work, of basically going down from a huge number of candidate materials, and then kind of using computational tools to rapidly filter down to a small set of candidates that they could then actually made in the lab, which is super impressive. Oh, by the way, if there's questions during my talk, please feel free to raise your hand. I also have some slides that I didn't put into the main presentation about Microsoft Research AI4Science. In case anybody's interested, just ask me after the talk then. Okay. So what's next after screening? Many people believe that there's roughly like 10 to the 10 or 10 to the 12 potential materials that you could make, but we have no idea which exactly those are. There's roughly 1 million, like 10 to the 6 known materials, but the space of things that we just haven't tapped into is enormous. And of course, screening doesn't help, because screening only goes through the database of stuff that you already know. So really the question is, how do you get from the known set of materials and how to tap into the vast set of potential materials that we haven't discovered yet. On the right is actually an animation of how our diffusion model works. So it doesn't go through just, it's not screening, it doesn't go through a list of candidates, but it actually designs new materials from like bottom up by randomly initializing a random material and then optimizing it. And I'll go into the details later. I talk a lot about materials. Many of you probably haven't heard about materials before. At least I didn't before I joined this effort. So we're talking about crystalline materials, which are solids in which the atoms form some periodic arrangement. So what you typically have is you have some unit cell. Let me actually go to the next slide. So you have some unit cell that is defined by three lattice vectors that we call L1, L2, and L3. And inside this unit cell, you have some arrangement of atoms that, of course, have some coordinates inside the cell and also have some atom type like carbon or iron or any other element that you can think of. And then the periodicity comes into play by kind of this unit cell repeats in all three space dimensions, we say infinitely. Of course, in practice, it's not infinite, but it's basically what we assume here. So you'll see me define a material as a tuple of A, X, and L later, and this refers to the atom types, which is basically an n-dimensional vector that just tells us for all the atoms inside the unit cell, which element do they belong to. Then we have X, which is the coordinate matrix, which is n by 3, which tells us where inside the unit cell is each atom located. And then we have the lattice L, which is these three-dimensional vectors that define the shape of the unit cell that then repeats infinitely in all three dimensions. Right. So the task that we have, or the objective for the model, is to learn a generative process over materials. And ideally, this generative process covers all the stable and even metastable materials. So things that could be stable under real-world conditions that form periodic structures in 3D. And there are some desiderata, of course. The generation process should respect the properties of 3D materials. For example, if you take the unit cell and you just rotate everything by 90 degrees or by 5 degrees, then of course the overall material is still the same. So we have rotation, invariance, and so on and so forth. It should handle the periodicity appropriately. So the fact that the unit cell repeats in the three space dimensions has some interesting consequences for the generative process. And finally, we'd like to be able to condition the generative process on conditions that we care about, like is it, how well is this material able to, capture carbon from the air, or maybe a bit more concretely, how hard is the material? So we would like to be able to tell the model, give me something that's like very hard or very soft, and then ideally the model takes that into account in the generative process. So who has heard about diffusion models before? Okay, very good. Then, right. So it's a very, very popular class of generative models that powers many of the AI image generators that you see on the web, like DALL-E 2. I think there's DALL-E 3 by now even. And the way that they work is, let me actually switch to the laser pointer. So you input a sample from your data set that's we call X0 here. And then you gradually add more and more noise into the image or into your data sample via these transition kernels that go from, for example, X0 to X1, and then from X1 to X2, and so on and so forth, until at the very end, at X capital T, maybe after 1,000 steps, you end up with a data sample that is distributed according to some very simple distribution that we know how to sample from. So basically, we destroy gradually all the information that's inside a data point, so that then after training, so we're training the model to reverse that destruction process, we can simply sample from this simple distribution at x capital T, and then use the model to like gradually fill in the details and denoise the initially completely random sample. For the case of Gaussian diffusion, so this is it looks like this. So this is one of the most widely used diffusion processes called DDPM, where the individual transition kernel from t-1 to t, it's just distributed to a normal distribution where the mean is on a scaled variant of the current noisy sample, and then you add some noise. And this is a Markov process, so at each step you only have to know what's my current noisy sample. You don't have to care about all the trajectory that came before that. And then finally you choose these coefficients beta t, quite carefully, such that in the beginning, basically there's zero noise that you add to the sample, but then as you go towards the end of the diffusion process, you end up with samples that are just distributed according to the standard normal distribution. So basically, this is not the only way that you can define a diffusion process. You have quite some flexibility in designing such a process. And there are just some important things, like you have to converge to a distribution that you can easily sample from, and you should ideally be able to compute the distribution of any arbitrary time step on the fly. So basically, you should be able to go from x0 to some, let's say, xt at 500 in one step, instead of having to go through the whole trajectory that leads you there, because that will make the training a lot slower. Okay, so this is what it looks like, how we designed our diffusion process for materials. So on the left, we see an input stable material that we denote by A0, X0, and L0, as we've seen before. And then we gradually add noise into both the lattice vectors, so they get noisier. As you can see in the beginning, we just have right angles, and then we go to some skewed lattices. So we add noise into the lattice. We also add noise into the atom coordinates, of course, and then we also add noise into the atom types, which are discrete, and I'll talk about the diffusion process there. So in the end, we have some completely random material that we can easily sample from this distribution. And then we learn a model that reverses this process. So the forward corruption process looks like this, and I'll tell you in a bit more detail what this means. So we want to go from some current noisy material, AT-1, XT-1, and LT-1, just to the next slightly more noisy material. And on the other hand, now the model's task is to take a noisy material and predict a slightly less noisy one, that if you unroll this for 1,000 steps or so, or maybe more, maybe less, then you end up with samples that resemble those that you have in the training distribution. Right, so as I said before, we have three components to a material: the atom types A, the coordinates x, and the lattice L. And for each of them, we define their own diffusion process, which evolve independently. So given the input material, all the three corruption processes, they completely go forward independently, so that they don't know about each other. And for the atom type diffusion, we use a process that's called D3PM, which was published at NeurIPS 2021. It's conceptually quite simple. So what you have is you define a Markov transition matrix. So this is now all the discrete case. So we have a transition matrix that goes from the number of classes we have to the number of classes we have, that just tells us what's the probability at this time step to go from, let's say, the atom type carbon to the atom type hydrogen. And we again have to define these transition matrices such that they basically destroy all the information that's encoded in the input sample. And the way, or the variant of this diffusion that worked best both for the authors of the paper, but also in our experiments, is what they call the mask diffusion, which is quite simple. So at each time step, you just have some non-zero probability that from, let's say, your type carbon, you go to some masked state or absorbing state. And once you're there, you cannot escape. So basically, a forward diffusion process looks like what we see at the top here. If you just look at the colors of the atoms, at some point everything becomes just gray, which represents this masked state that doesn't correspond to a physical atom type, but it's just a dummy state basically. And after all the diffusion process, you just have masked atom types. So that's where we start from. It's also particularly easy to sample from because you just set all the atom types to this masked state, and you feed that to the model, and the model learns how to fill in the atom types, basically. Right. So before going to the other types of diffusion, I want to talk about what's the actual model that we're using. So we're using a graph neural network. Who has heard about graph neural networks? Okay, very good, majority. So we use a GNN as a backbone, and the particular architecture that we're using is called GemNet. And this GNN model, what it does is it takes a noisy sample and it predicts the three updates, basically the denoising updates for the atom types, for the positions X, and for the lattice. And when I say score here, that's basically machine learning lingo for the gradient of the log probability. So what we're trying to learn here is some function that takes a noisy sample and predicts this quantity on the right here, which is for the Gaussian is known in closed form. So it's just a regression problem basically. And of course the GNN's supposed to match well the data that we look at, or that we have at hand, the 3D materials. So we call it an equivariant score network because its predictions change in a predictable way if, let's say, you rotate the input. It's quite easy. If you rotate the input material, what would happen? The model would just rotate all the predictions in exactly the same way. So that's what equivariant means, and invariant just means nothing happens. So of course, for the atom types, it doesn't matter how you globally rotate the material, it will just predict the same update for the atom types nonetheless. Right, so let me go back here to this representation of the unit cell, because that's what took me a bit to kind of appreciate what this periodic representation actually means for the generative process and how to model it appropriately. So the first thing is, so I can't draw so well, so this is all in 2D now, but I trust you can imagine that there's a third dimension in the things that we actually care about. So imagine that, we have this very simple 2D material, which with some atoms, and the color indicates the atom type, and we have two lattice vectors, L1 and L2. So this is now the unit cell in 2D that we've just seen in 3D before. We have a GNN as a backbone. So one of the graph in GNN kind of suggests that we have to construct a graph for the input data point that we have here. And the way this usually works is that you look at each atom and you look into some cutoff radius, let's say 7 angstrom, and you just see which other atoms are within that cutoff, and then you just insert an edge. In this very toy example, let's imagine that we just connect with all the atoms that are right next to it. So this will be the nearest neighbor graph that we build if we just look at the unit cell and take it as it is. But this is not the correct way to build a graph for a periodic material. And the reason is that this representation, if you just look at it, what you miss is that you actually, this thing extends in all directions infinitely. So there's no reason why there's no edge between this atom and this one, because it has the same distance from this one as this one to this one. So it's exactly the same distance, but we don't have an edge. So this is not the right way to kind of build a graph for an input material. So the way that we do this, and people have figured this out before us, is that you build a periodic nearest neighbor graph. So you also look, when you, let's say you take this atom on the top left, you don't just look inside the unit cell, which atoms are within the cutoff radius, but you also look into the neighboring cells, so kind of the repetitions of the unit cell, and you check which atoms there fall into the radius, and then you also build an edge there. And this means that you can have multiple edges between the same atom, because, for example, you could in principle have an atom from the orange one to its next image in the neighboring cell if, let's say, your radius is large enough. So you also have to keep track of, you basically have another index that tells you this is an edge between atom I and atom J, and you basically cross the periodic boundary that many times. So by default, you would have it all 0, but you could also cross, let's say, the first periodic boundary one time, and you just store this extra information. And then what does this mean for let's say, diffusion process on these atoms? So again, this is a 2D toy example with a unit cell. Again, we repeat in all 2 dimensions infinitely. Now, what if we want to move this blue atom, according to this arrow here? This would actually mean that we don't just move this one, but because all the other blue atoms are just replicas of the one inside the unit cell, we also have to move all the other periodic images exactly the same way. And if we do that, we end up with something that looks like this. And if we just look into the center unit cell, what the result of this movement, so we kick out the blue atom out of the unit cell, and the result of the periodicity is that it just re-enters the unit cell from the right, because implicitly to the right of our center unit cell, there's another one from which the atom will be kicked out to the left, so it ends up inside the unit cell. So this has some consequences for what corruption process we actually use to kind of handle this wrapping. And then also, what happens if you now have this unit cell and you change the lattice? So let's say we just enlarge the second cell vector, that's the vertical one. The result of this would be that all the vertical distances of the atoms get expanded. So you just expand everything in the vertical direction. So also the lattice deformations also affect how the atoms are placed inside the unit cell. Right. So it ends up, if you look at if you think about what would be the generalization of just applying, just adding Gaussian noise to an atom under the periodicity constraint, what you end up with is the so-called wrapped normal distribution, where you just basically you take the probability mass that overlaps with the periodic boundary and you just add it from the right. And it's a well-studied distribution. It has some nice properties, but it also has some not so nice properties, which is that if you want to evaluate the likelihood of a sample, you have to evaluate this infinite sum, because you have to, in principle, you have to, because the Gaussian has infinite support, it could happen that your atom gets moved, gets displaced into a unit cell that's, 3 trillion unit cells away from your center unit cell. So in principle, you also have to add up the contribution from that unit cell very, very far away. But, knowing Gaussians, the good thing about this is that it has thin tails. So we can just use a truncated sum and we get a very good approximation of the likelihood. So for the lattice, there's just one nice trick that we had to use here, which is that a lattice matrix that has three three-dimensional vectors is a 3x3 matrix, so it has 9 degrees of freedom. But if you look at material science textbooks, you will only, and you look at how is a unit cell defined, you'll only find 6 degrees of freedom. So you have 3 lengths. So each vector would be represented by its length, and also you have the 3 angles between the lattice vectors. So you think, why do we have 9 degrees of freedom now in a 3x3 matrix? And the answer is that we also have the rotation degree of freedom. So we could, 3 degrees of freedom just define how we rotate the lattice, and the rotation is completely arbitrary. It doesn't change anything about the material. So the way that we kind of get rid of this extra degrees of freedom is we use the so-called polar decomposition that works via the singular value decomposition, that you can give it any positive definite matrix, and it'll just output you a matrix that is symmetric. So now we only have 6 degrees of freedom left, and it also outputs a rotation matrix that we just throw away. So we basically only work in the subspace of symmetric matrices. Okay, I'm running a bit out of time, so I'm going to skip more of the details, and I'll get to some training details. So what's the data that we train on? And basically, we tap into public sources of hypothetical and real materials. So there's the materials project, which is very widely known. There's ICSD, which has lots of materials that people have been able to actually make. So this is a very high quality data source. And then there's also the Alexandria dataset, which I think comes from some research group in Germany. And we apply some filtering, so we only take things that have. Oh yeah.
My question is, this 1.08 million of reference data are generated or are real data that are existing materials in the nature or whatever?
Both. So the majority of them, I think, so the material scientists could say this better, but the majority, I think, are hypothetical. So people have come up with an arrangement inside with a unit cell arrangement of atoms, and they've used computational tools that basically tell you how energetically favorable is this compound. And only if the answer is, given the best computational methods, this looks to be quite stable. So it's very likely that this thing could exist and wouldn't spontaneously decompose into more energetically favorable states. Then people add it to such databases typically.
Okay.
And the core problem here is that that given material that you have on your computer, maybe that's generated by a model or you get it otherwise, there's really no way of telling whether this thing could be made. You can use all the computational tools that give you estimates of how likely it is that it could be made, but in the end, somebody has to be able to go to the lab and make it. So it could even be that that in principle one could synthesize this material, but we just don't have the tools to, not the right processes discovered yet. So this is all possible. So maybe some of the hypothetical materials will be synthesized maybe 10, 20 years from now when we have better methods in synthesizing stuff. So anyway, the bottom line from this slide is that the training data that we constructed is about 15 times larger than the most popular kind of alternative data set, MP20. And we'll see how that affects the results. This is just some non-cherry-picked samples that come out of the model. So to me, it looks nice. We have some nice symmetries in there. And also the material scientists think these are quite reasonable. A key question that this other question already hinted at is, how do we evaluate a generative model? It's very hard because you just have samples, but you don't know how good they are. The good thing in science is that we have lots of computational tools that tell us more about the samples. So we use density functional theory to estimate the energy of the compound and compare it with competing phases. So basically what we're interested in is what's the fraction of stuff that we generate that's both stable or predicted to be stable, unique, and novel. Because if it's not novel, then why would you generate it? So that's kind of this SUN, stable, novel, and unique. That's our key metric that we look at. And going from CDVAE, which was kind of the previous state-of-the-art, just to our new diffusion process and model architecture that we're using, you get like a 1.5x improvement. But then a really large jump of another almost 2x improvement comes just from going from the small MP20 dataset to the new dataset that we've constructed. And this slide basically tells the same. Now, I'm basically out of time, but I just want to highlight that we also look at conditional generation, where basically you give the model you train the model both on unconditional samples, but you also give it some samples that have a property label attached to them. Let's say this material has a certain bulk modulus value, which tells you how hard something is, like diamond is very hard, for example. And you learn both of them. You learn just one model at the same time. Sometimes you give it the condition, sometimes you don't. And what this gives you is you basically get a conditional score network that gives you the score of M conditioned on C, where C is your property value. And you also, of course, have the unconditional model. We use fine-tuning to do that. And this is a very exciting result that we got. So on the blue greenish distribution is just the baseline distribution that we have in our labeled dataset for the certain properties. So we have magnetic density, band gap, and bulk modulus, which tells you how hard something is. And the dashed line tells you what's the target value that we want the model to generate. And what's really cool is that you can really get the model to generate stuff that's way out of the kind of the distribution that we have at hand. So there's basically almost no support at 400 bulk modulus in the training dataset, but still the model is kind of able to go there. And this is all verified with a DFT-based workflow. So yeah, pretty solid computational method there. Yeah, this outperforms screening now. So of course, screening, you go through a dataset and you just check each of them how well they score on a certain property. At some point, you're going to exhaust all the promising candidates. So in the beginning, the blue line screening is basically competitive with our method, but at some point it just starts to saturate because there's no more promising candidates in the dataset. And this is where the generative model starts to shine, because we can just keep generating stuff and kind of we don't see any sign of saturation there yet. This is another use case example, which I'm going to skip. So with this, thank you for your attention, and I'm happy to take any questions.
Okay, thank you for this awesome talk. Now, I would say we do maybe 15 to 20 minutes of questions. If you have a question, please raise your hand and Lorenz will give you the mic. Thank you again.
Just want to know, how large was your data set and how have you tackled the hallucination and accuracy problems?
Well, so the data set that we trained on was roughly 600,000 samples. So in LLM dimensions, that's tiny. In science dimensions, that's actually, it's 15 times larger than what people have been using before. So it's quite large. And hallucination, well, it's like in science, the question of hallucination is a bit different than in LLMs, because in the end, if the model hallucinates something, it could be good. And if it does, we can use we can detect it with the computational workflow. So if the model generates something that's just garbage, then hopefully, we have pretty good computational tools available. They would kind of tell us, oh, all the stuff that you're generating is not stable. It could spontaneously decompose if you would try to make it. So that's one of the good things when you work in the science domain. You don't only have to rely on basically humans looking at the samples, but you can use a lot of machinery that's been developed for decades that kind of tells you a bit of how good samples are and what properties they might have if you make them.
Interesting. Would you reveal your base model?
Whether we would publish it? Well, we're in discussions whether we can open source, but Microsoft is a big company and it takes some time. But so right now, this is purely research. We just published the paper in December. Yeah.
You mentioned that you verify your results with DFT calculations. Can you elaborate on that a little bit?
Yes, I can elaborate a little bit. So we use PBE functional and basically run a double relaxation with the static calculation in the end. And then we filter by a cutoff of 0.1 EV per atom above the convex hull, basically taking into account the reference data.
Okay, which
And we're using VASP.
Okay, if you have follow-up questions, let me know so I can give you the mic.
Hey, I just want to ask, you created so many materials through the simulations. Did you run DFTs on all of them or just on the select few?
Fantastic point. I didn't get to talk about that. We use a machine learning force field to basically, so we take the samples, we relax them first with a force field that's very cheap, but reasonable high quality. Then we get the energy prediction for the relaxed structure. And then we basically have a first filtering step. So in the end, we care about 0.1 EV above the convex hull. For this intermediate step, we're a bit more generous. I think we have like 0.15 or 0.2 EV above the hull. But that already kind of gets rid of the bad samples that the model generated. And only those that make this first filtering step are sent to DFT.
Hi. Just could you quantify kind of how many computational resources did the TFT take in comparison to the training or the inference in the end?
That's a good point. So there are very different types of workloads. So the DFT runs on CPU, where training obviously runs on GPU. So I know for the bulk modulus if you want to estimate the hardness of something, that's very expensive. So one single structure can take a day on a compute node. The DFT energy estimation and relaxation are a lot faster. I don't have any concrete numbers, but most of the DFT relaxation jobs finish within, let's say, 2 hours. Some of them run for like 24 hours or longer, but the vast majority is relatively fast to converge.
My question is regarding the novelty, seeing as it's kind of a key metric. So I know you showed that in any case, conditioning can be used to kind of increase novelty, but are there any other knobs that you can tune? Like what do you do if your model comes out and the novelty score is a bit low?
That's a good point. So I guess, so one thing that you could clearly do is you could try to detect overfitting during training. So most likely you would, if the model really just regenerates mostly stuff from the training data, you would kind of see that in the loss. So kind of validation loss goes up or something during training. So that would be something that you can do during training or before you actually take the model. And then during sampling, you also have a bit of freedom there. So you can use different basically integrators that go from the random structure to the sampled one, and you can kind of inject a bit more noise there if you use different samplers. So that could be something you could also try. And other than that, I'm sure that there's a ton of papers on this, but that's basically how we've tackled it so far.
Have you found anything yet where you would be excited to see in a lab or try it out?
That's a good point. So we have a bunch of the highest quality results. So basically, we have some stuff that's predicted to be not just to be metastable, but predicted to be actually stable. So under the currently known convex hull, we have some of those in the paper. So those will be. I'm not a material scientist, but those would probably be the ones that I would be most excited about. But I think that's as much as I can say.
Yeah, thank you for your presentation. You already mentioned that you explored classifier-free guidance. I was wondering because I'm not sure if you're familiar with Rosetta Fold Diffusion or like some of the protein engineering models. They also use classifier-based guidance or heuristic approximations. And I was wondering if you also explored that or if that's interesting in inorganic materials at all.
So we haven't given this a shot yet. it's definitely worth trying. It has some nice advantages, like you could just have one unconditional model, and then for each property, you just have the classifier that you then use for the guidance. So that's super nice. One thing that's a bit tricky, at least for our use case, is that we have these discrete atom types, and it's a bit hard to define, like what's, the gradient with respect to those is undefined. So you'd have to kind of find a trick around that if you actually want to use the model to also fill in the atom types. But yeah, overall, definitely interesting.
Thank you for your presentation. So I'm curious. So periodicity is a big constraint in all the construction of the new materials, and there are some quasi-periodic materials, so that there is a crystal structure that is not periodic. How easy can you kind of extend your work into generate quasi-crystals, quasi-periodic crystals?
That's a very good question. I don't know the answer. I don't know exactly how quasicrystals work, but I would be surprised if there's no way to incorporate that into the model. But I would have to look into it.
Okay. I have a question. That is, does it help to get more stable elements if you start from a material and only run a diffusion process for, like, let's say 20% of it and then reversed it?
So we haven't tried it. I wonder. So basically, on expectation, what you would have done by then is you would have deleted 20% of the atom types, and my intuition is that the remaining information that's still in the 80% might still be enough for the model to just trivially know what has to be in the blanks, because there's a lot of symmetry in the data. So many of the crystals have something like a mirror symmetry or rotation symmetry. So if you only mask, let's say, one atom, but you still have its mirror image unmasked, then the model could trivially know, okay, there's probably a mirror plane here, so I'm going to fill in whatever is on the other side just there. So you probably have to go maybe to 50, 60, 70%.
Thank you. Okay, so I think we come to the end, unless there are some other pending questions. Okay. Yeah, then once again, a big applause for Daniel.